So thank you for organizing. Thank you for having me. Fun fact, I was actually born and raised in Belgrade, did my undergrad there, and this is my first time in Novi Sad. So, so thank you for bringing me to Novi Sad. I also then immigrated, had non-traditional research career, and so on, had full immigrant experience, did my master's, worked, did PhD later on, and so on. So if anybody wants to talk about weird career paths, I'm going to be here all day today. So with that, today I'm going to talk about fun stuff, autonomous agents. So what are autonomous agents and why talk to them? So there was lots of talks about this morning about reinforcement learning, Bayesian, right? There were all these topics. When it gets to autonomous agents, really, this is where things come together from different fields and how to have them work in real world, right? So what are autonomous agents? Like any systems, right, that does and interacts with the real environment, real world, and does something, changes the world to some end to accomplish a task. And we can kind of look at the robotics, we can look at the autonomous vehicles, cars, or even the web agents that basically they go in, manipulate web environment or manipulate kind of drive in the real world. And they share similar challenges. And this whole talk is going to be about different challenges and how to overcome them. At a higher level, so what would be a scalable autonomy, right? How to do this in a scalable way to enable these systems fundamentally and develop methods, right, that enable this work. The key question is how to efficiently train agents that bring these high-performing general agents in the real world. So they're roughly, I mean, you can slice it and dice it in many ways. One way to slice it is that we want high-quality behaviors. So safety is important, right? You have a self-driving car, we don't want it crashing into things. You want to have generalization, which means that you don't want a unitasker thing that robot can go from A to B, move left to right, or just pick up this object, right? We want to generalize to, and then what that is. Is it different initial positions? Is it different tasks? Is it different environments? Where does the generalization come from? And then all this needs to be tractable because we can dream big, but when it gets to fixed computational budget or training time, right, and so on, or memory or whatever, it needs to be feasible. So that's basically like roughly three sides of the triangle, and the real-world autonomy is kind of sitting there in the middle, basically doing all three. And traditionally, we've been addressing the edges of the triangle, so I have three parts to the talk. First is like how we've traditionally been addressing this, through addressing the sides of the triangle, having the efficient training, having the efficient generalization, or the high quality but really expensive generalization, right? But that middle has been eluding for the longest time. So first part of the talk, I'll give one example just to kind of give you an idea of how these topics have been traditionally addressed. The second part, now I'm going to start talking about the generalist agents. Last few years have been seen the merging of these models, right, that can do more than one thing, and this is kind of starting to get feasible. We're going to kind of take the data angle as how we can get these generalist agents to improve upon the data that they were given on. And then finally, going to look into how LLMs, large language models, and the autonomous agents fields can help each other, where they play that's kind of more future looking. I'm going to cover lots of ground. The idea is not to it's more to kind of give you the breadth of the ideas and kind of how to think and give you the vocabulary than kind of go into depth for anyway. So if you don't kind of follow and so on, can chat offline, there are references, and feel free to interrupt me if you need to, and so on in questions. Okay. So the efficient training, this would be your bread and butter of reinforcement learning. And the earlier talk that Hazan has given on various algorithms from DDPG and then PPO, right, and so on. How do we get agents to do and improve and interact with the environments? The offline RL is one of the kind of more recent directions that is trying to kind of merge the supervised learning with reinforcement learning, where the idea is that you have some data set and then you basically do apply the ideas of the RL. One example that I just want to highlight is the safe navigation, is Lyapunov-based safe policy optimization, where we're saying, hey, you don't need, reward is not enough. Oftentimes you actually have some system constraints that you want to satisfy. And in this case, we're evaluating on a number of other things. But in this case, just as an example, if we have a robot that needs to go from A to B, well, maybe we want to kind of have the fixed budget for how much energy to spend on collisions. Granted, we don't want collisions, but heads-on collisions are bad. Brushing off things, well, maybe it's fine if it can find other things, right? The other way you can kind of think of it, you can pose it, the constraint over the trajectory is the battery. Give me from A to B, but using only 20% of battery, because otherwise I'm going to run out of battery and so on. And the idea here is that the value function is a Lyapunov function, so it kind of keeps you in the constraints, and it only kind of allocates a little bit of the budget as you're going along the way, in addition to optimizing for the reward. And it turns out that the TRPO that was mentioned earlier today is a special case of this algorithm. And you can kind of see how the actual trajectory performs better. The efficient generalization is all about training finding a ways or clever ways to construct training environments and the data for real world. And there is lots of work there in terms of how to bridge sim to real gap. What's sim to real gap, you would ask? Well, your simulation environment that you use for training, and then you take that policy, you plop it on your robot or so on, and you kind of get it onto real environment. And sim to real gap is how do you bridge this gap from simulation to the reality, and so on. So one just kind of illustrative example from that is our work with Claire Tomlin's lab at Berkeley. We're tackling visual social navigation. And the task is here that you have a robot that has a visual camera, so it gets an RGB image. And we want it to go from A to B and avoid people. How do we train this practically? You have two options, right? One option is train on real environment, basically have the robot in a crowd of people and hope for the best. How many volunteers you're going to have for that? Not to mention kind of diversity of humans and so on. But visual transfer from simulation to reality is a big problem, right? The other alternative is to train in simulation, but then what's your fidelity that what you're kind of having in simulation is going to work on real world? So in this case, the way we tackled it, we construct an environment that we take a data set of the buildings, which we know transfers sim to real, that if we train models in this environment, the visual characteristics match. And then we also take another data set of the humans that kind of has the human representations and how humans, and we parameterize humans. We parameterize their height, their speed, their behavior, their skin color, right, and all these things. And we combine these, and now you can randomly see the environment with, hey, here is this office building, and here is this person and where it's going, right, and so on. Now you can play. So that's the first step, creating this environment. Beyond that, now kind of getting into a second step, and this kind of recipe follows for a number of other works that kind of goes in this self-supervised learning. So now that we have environment, that environment has privileged information. And we want to learn the policy and how we do that. So first step is data collection. In the privileged environment, we randomly initialize poses and so on. We let it run. In this case, we're looking to, when we're doing the planning, and the robot is trying to decide where to go. So if the goal is to go towards the door, and I have a person here, do I want to go behind them or in front of them, right? So I kind of need to decide on these intermediate waypoints. So we create, basically, randomly kind of select the waypoints. We solve this with the privileged information and create a data set that says, here's my image, here is the waypoint, here is the cost for the waypoint. From that point, next we can create a predictive, like a model. Predictive model says, for the image and waypoint, here is what I'm expecting the cost to be. This is where the generalization happened. And then once we have on the robot, we don't need any more the privileged information. Now we have the predictive model that then when I deploy it on the robot, I can say, hey, okay, if I see a person here, do I go left or do I go to right, and selects the waypoints. And elegantly kind of solves this both privacy and the safety concern when it gets to deploying to the real world. So here are just two examples. Here on, let's see. When the human is static, the robot goes in front of the human. When the human is moving in this direction, the robot decides to go behind. And what basically it implicitly learns to associate the leg position and the direction of the feet with the motion, and basically go for the safer behavior. It doesn't know where human is going, how fast, right, and so on. So this is when we're getting into the edges of the generalization. And you can kind of see the example. This is a zero-shot transfer with the difference that the camera in simulation had a 65-degree angle, and here it's 45-degree in reality. So it goes a little bit off the course, but it avoids a person. This is the prior work that ends up in a collision. So the method works, but not when people go behind. All right, so the high quality generalization, these are expensive methods, right? And things that I would put in this bucket are things like meta-learning, learning to learn, AutoRL, multi-agent learning, and so on. So example that I'm going to talk about is about curriculum learning, when we're kind of having two networks that kind of teach each other. And for that, I'll go and talk about in the context of the web agents. So the task here is your form-filling task. However many times you kind of did one-click Amazon, both checked in, right, and so on, did the form filling. It turns out the task is actually very similar to your robot navigation and manipulation task. You manipulate the environment, you hit the submit button, you appear in a new room, right? New world. You again need to manipulate the environment to solve the puzzle, hit the next submit button, and kind of go through several pages. So it has lots of similarities with the autonomous manipulation task, except that the benchmarks at the time, and largely today, are very simple. 100 DOM elements were like this is a Southwest page, had something like the order of 30,000 DOM elements on the page. And at the time, when we started looking at this, which was about 5 years ago or so, the models were only solving single form with the millions of examples per form. And the form is this thing on the left. So hardly ideal, and doesn't scale. Like if I need to spend million iPads to make a mistake, that's costly. So what we ended up doing, this thing that bugs me and kind of answers your question to a certain extent, is how do we know what's generalization and what we can expect to generalize and what we cannot? How many people have heard of Petri nets here? Okay, more than. Roughly, Petri nets are graph representation that can represent workflows. So we attempted to say, hey, okay, at least for this set of tasks, because in reinforcement learning, you have Markov decision process or POM MDP, and says, okay, we're solving that. Well, where's generalization in that? Like there's nothing in that definition that says anything about generalization. So we say here, okay, if I start with DOM elements like a drop-down box or input box or a submit button that can, or a calendar thing, date field that can be a calendar or drop-down or an entry, it can kind of represent itself in many ways. I can construct a workflow. I can construct a family of the workflows that's described by this PetriNet mechanism. And then we can say that, okay, with the 45 primitives, or however many, this is how many tasks I have. Each task corresponds to one POM-MDP formulation. And our task, if we want to have one agent that basically solves any form-filling task, is to basically have an agent that solves the expected return over this family of POM-MDPs that's induced by the graph. It is an attempt. It is an attempt just to say, hey, if we do form filling, we cannot solve robot manipulation, right? Because this is what we trained it for. From there, we can then if we kind of have this definition, we can start creating generative environments. And in order to solve it, we basically do two networks. One is designer, LSTM, that generates the environment. And its job is to basically create just the right challenge for the training agent. And here is an example of kind of rolling out the training agent is the RL agent. It operates in this environment that's basically presented to it. Its actions are to manipulate the fields. And its reward is whether it completes the task or does not. It feeds back to the designer how well it's done, and basically we're training a family of them, bunch of them, so we can kind of see how's the best agent performing, how's the worst, how they're doing at the average. So regret here is the difference between the best performing and the worst performing agent, and then we're also kind of feed the best performing agent. And these two signals go back to designer to then adapt whether to make it harder or make it more difficult environment in the next step. And then we evaluate on the held out set on basically real websites that were not auto-generated. What we get here is that as the training progresses, the environments become more complex. And these other two, so blue one is the curriculum, the other one is manual curriculum, and I forgot what the other headline is. I think it was just kind of randomly selected data. We see them that they generalize to the unseen environments. And as the training changes, the designer network is learning that some elements are more important for task completion. So if you don't have a submit button, which is kind of important for the form filling, you're not going to finish the task. At the beginning, the designer network doesn't know that, but then it learns that along the training process. So that's one way, and it's more expensive because now you're training two networks and so on. I'm sorry? The input for the agent is basically the environment, the DOM, like the HTML for the HTML text. Yeah. Yeah. Basically, with this whole web agents line of work, I know there's lots of work with using the images and whatnot. We opted to do HTML because it was easier to work with text than to have a renderer on the server side to display images, and it was like, okay, let's see how far we can get with the. All right. So this is kind of how traditional we've done things. Now, with the recent kind of advances, we're starting to tackle the middle of it. Something with the transformers happened in the last few years, and I'm not going to spend too much slide, and there's going to be a whole talk on the transformers. And I updated this 2 years ago, so things like the retrieval augmented generalization is not here to use and so on. But just gives you kind of the idea of the rapid progress, how it started from basically transformers becoming the architecture and the attention becoming the architecture, to then starting with the birth of the first LLMs, a GPT class, right? And then kind of starting getting into the using transformers for the planning and sequential decision making. How do we kind of get the trajectories of the how to learn the trajectories, not just the sequences. So decision transformers came in, and scene transformers. I'll talk about that a little bit more. At the same time, the LLM started growing. Then we kind of saw the first foundation models for robotics, such as Gato or Seiken. We started seeing kind of more generalization on the multi-game decision transformers. So your question around the Atari games, right, being separate versus now we can have a single model. I'll talk more about that, and so on. And now, kind of 2022 or so on, we're starting to see emergence of more of the text to video or text to image models as well. And now we're kind of getting into more actions space. So when it boils down to machine learning, there are three things. There is the architecture, there are objectives, and there is data. You can kind of go fine-grained, but like at the 30,000 feet, that's about it. So architecture is whether it's your transformers, right? It's going to be whole talk. For the purposes of this, kind of in the next few slides, I just want to mention there are roughly three main uses, I guess, you can do. You can think about the transformers, whether they do sequence-to-sequence translation. So for example, if you say transformers are not a toy, you can translate it to French or whatever and kind of gets a whole sequence. There's the next token prediction, which is kind of what we hear nowadays most, your GPTs and Geminis and whatnot, where you say transformers are not, and then kind of predicts toy as the next token. And then there's the mask prediction, which you give a whole sequence and you have a special token that is a mask, and then basically the model recovers the missing. So that's all from that perspective. Objectives are about your loss functions. In reinforcement learning, are you learning value function, or are you doing the policy optimization using Bowman update, right, or so on, how you're doing that optimization. If you're using imitation learning or behavior control, then you're optimizing not for the reward, but for the next action, and so on. And then there is data, the unsung hero of machine learning. Something that traditionally machine learning research community just assumed data is there, environment is there, until you actually start dealing with real data and so on. And I think as a community, we're starting to say, hey, we should look into this. So I think there's a lot more work and research and PhD thesis around the role of data and how to use the data and so on. So for the next few slides, I'm going to kind of go from the data-centric perspective on kind of where the generalist agents are going. So first, generalist agent through imitation. With the imitation, by the default, you have some data. Your models will not perform better than the data it was given. There is also the fact that imitation data tends to be expensive, right? And like, okay, but there is an expense also on how designing simulation environments and whatnot, granted, and it's not apples to oranges, but I mean, it's something to know. So one of the first models that I mentioned in the prior slide is the scene transformer for the autonomous driving. And here our colleagues did this. The idea is, how do you represent the scene? And the scene was represented with the vehicle, all the vehicles that are on the road, everything that we know on the road graph, and it outputs the next, like what happens at step t+1. And it was using this masking architecture, where then you can mask, once you kind of train the model, you can mask and you can use it to ask for different predictions. So if I mask the self-driving car and I see where all other agents are doing, it can kind of predict me where self-driving car is going to be in the next step. If I mask, I don't know, other car and trying to turn left and know where the car is going, right, and so on, it kind of predicts me what is most likely that the other agent is going to do, turn left to right. Or I can ask it, okay, where is it going, what is destination, and so on. So that's kind of pretty cool and useful, and was one of the first methods, right, that actually made difference in autonomous driving from the generalist perspective, because it was so flexible. But the question is really, how do we go beyond the imitation? How do we get better than the data that we're having? And one of the forks that kind of built on the Atari games, the decision transformer first came in to say, hey, okay, if we're using this transformer architecture or masking transformer architecture, we can represent the data in this SARSA sample. So state, action, reward, next state, and kind of keep doing that. And we're doing the masking architecture then if I'm asking to predict what the next state is going to be or what the next action should be. Nice thing about that is I can also ask, I can basically task it with a reward. If the reward is not, you can kind of predict me what the reward is going to be, but I can basically task it. But turns out if you use decision transformers, and instead of just training it on a single game, if you train it on all, I guess in this case, 41 Atari games, it's going to learn how to play all the 40 Atari games, pretty much as well as the specialist agents are. Cool thing about this is that if you add about 1% of the new data for the new game, it's going to learn the new game as well. And you can kind of see down what it's paying attention to. Now, the limit is here, it's using the variety of the data from the expert to the novice data, so you don't need to have all the expert data. So that's better than requiring all expert data. But also, it's a nice thing that you can say, you can ask it to play at basically novice level if you task it with a low reward versus higher reward. The other kind of fundamental thing about the data that, I'm going to go back to that cherry on top slide, Jan LeCun's, it's a heavy cherry. There is lots of data, not all data is created equal. Take autonomous driving. Pick any data we're having. You have tons of boring data. Tons of data driving on the road where there's nobody around. How much data you have of dangerous situations where you're in a collision or near collision and so on. Can you get more data that's high stakes, critical? Can you ethically get children on the road running in front of the car? No. So, not all data is created equal, and it's a fundamental property of the high consequence systems that we have giant holes in the data that we don't have access to. Right, so let's kind of turn that to a research problem and say, how can we design learning methods, right, that take the advantage of that fact. So to that end, we propose combination of the reinforcement learning and imitation learning. So the idea is that basically when you use imitation learning, and while we're in the distribution, it's going to rely on the imitation learning. Once it starts kind of getting outside of the distribution for the imitation learning, we have a reward, which is safety reward. It's going to kind of kick in, and then reinforcement learning is going to kind of use that. So if we do that, the model was trained on 100,000 of urban real data that Waymo had access to. It's open source, I believe. It improves the safety without compromising human-like behavior, and I'll come back to that. So in this graph, the lower is the better. The blue and red are imitation learning methods, and then yellow is the behavior cloning soft actor critic, so this combined method that it's using. And we see a significant reduction, especially in the most critical scenarios. And you kind of see a couple of examples on the left where the standard behavior cloning would result in the collisions, whereas this combined method would not. So there are kind of a couple of tricks there to get it going. We're using the transformer observer encoder. We're training only on difficult examples, which actually kind of proved to be the case. So boring data you really don't need. We're using this mixture loss. And then reward is basically safety reward, don't collide and stay on the road and so on, you can kind of make. Now what's interesting about this is that when it gets to these autonomous agents, policies, robotics and so on, go from A to B, getting to the destination is hardly ever the answer. There is a lot about how you do that, right? Nobody's going to go for the shortest path. If I went to the shortest path, I would kind of be touching the walls, right, and so on, and nobody does that. We're kind of keeping some safe margin, whatever safe margin is. There are traffic rules, there are lots of kind of inherited behaviors. Say in the web browsing thing, you can expect your agent to fill the fields in the order they're showing up and not go randomly, right? And that user experience is going to matter a lot. In autonomous driving, if you left it for RL to just say, go as fast as you can, you're going to be slamming on the brakes and slamming on the gas all the time, and after lunch, don't recommend it. So what's interesting here is that this combined method then takes the best parts on how of the learning, which is very hard to describe through the reward, from the behavior cloning, and then takes the safety part from the reinforcement learning. So take acceleration. So this is the acceleration. The blue one is how humans do it, and then this is our combined policy. Sure, it breaks more on the edges. That's the safety part, which is where behavior cloning policy does not perform well. But then if you just left it to reinforcement learning, you would get like as fast and then stop, right, and lots of jerking behavior. And same goes for the tire angles. So that's very promising, because that's one way that we can combine best of both methods. Now, when it got to the reinforcement learning, so this still uses some expert data. And again, expert data, great when you have it. The holy grail is, well, I would like to be able to train an agent without any expert data. So that's kind of where RL should shine. However, it turned out that scaling reinforcement learning to the large capacity model was pretty elusive for the longest time. There's a number of reasons. Maybe it all can be distilled to the fact that by the definition, reinforcement learning is not IID method. Learning in the loop with non-stationary environments and non-stationary data, your distribution is always changing. It's always, so the fact, and then you're having this sequential causal states that do depend on each other, as much as we say in the MDP definition that they don't, they do. They are very near to each other, so the consequent states are very similar to each other, but the model still need to differentiate them when it needs to, but not differentiate them when it doesn't. So it turns out that the benefits that the supervised learning benefited from increasing the capacity of the models and this implicit regularization and so on really did not work in the reinforcement learning. So there was a number of things, regularizers there to put going from the regression to the classification laws, the cross-entropy laws, and a number of kind of improvements that were finally at a point that we can use the reinforcement learning and train the superhuman performance on kind of generalist agents without expert data that outperform what the data is. And here are some examples here for Atari games, for chess, for Wordle game, and for some kind of robotics picking tasks. And again, in kind of domain, we also see that about 1%, adding 1% of the data can generalize and learn new game. Again, this is without expert data. So we're starting to get there in terms of the reinforcement learning. So when we kind of go back, what are some general themes and observations that we see? that across the domains and across the architectures and so on, the model size matters. And generally, that tends to be that the bigger is better. Depends which application, which architecture, how much gain you get from the scaling increase varies, but the trend is the same. It also seems like a fine-tuning, which basically means, okay, you have some pre-training model, and then you're going to add more data to it and then update weights. That fine-tuning generally requires 0.5% to 1% of the data to basically acquire a new skill or whatnot. The other aspect of the scaling is the data matters. There was work that showed on RT1, on the robotics task, that decreasing the data, so if you're going to remove the data, which data you remove matters. So as long as you kind of preserve the diversity of the data and kind of basically the span of the data that's given, you're getting very little hit in the performance. And if you kind of have this visual from back in Waymo, lots of boring data and not good data, you can safely remove lots of boring data, right? The second aspect is slightly interesting, and this is kind of comes down to the curriculum. If you think of it, the curriculum that I talked about on like few slides back about agent generating web pages and then training and so on. So that would be a blue curve, and then red curve is the manual curriculum, and the green curve is basically just randomly presented. We're pulling data out of the same distribution between these three lines. Oops. We're pulling data out of the same distribution for these three curves. The only difference is really which data sample we present to the training agent at a time. So let it sink, right? What it means is that how well your agent is going to turn to learn, it depends what sample you presented, or to turn it around, the sample that you presented, it needs to be kind of contexted on the current state of the agent and what it knows and what doesn't know, what's ready, and so on. We're also seeing this kind of in some of the newer work, where I'm kind of calling now this Goldilocks principle, that if you present the data that's too near the distribution, you're not going to get gains. If you kind of present a sample that's too far off, you're going to get lost. But there is this sweet spot somewhere in the middle, and there's lots of work that I think needs to be still done on what kind of these similarity metrics, right, and the distance metrics and so on need to happen to know. But if you kind of hit that middle spot, they're going to start self-improving and learning better. So this raises question, right? If you have fixed budget or fixed time, right, and so on, do you invest in better data, cleaning up the data, nurturing the agent with the data, or do you invest it in what I called agent's nature, the architecture, loss functions, right, and so on? And it's not clear really from the fundamentals now. I think that's really emerging. Will be emerging science in the next few years, right, and so on, was that interplay and when to do one, when to do other. All right. So this is promising. Are we done? Can go home and be done with it? AI solved? No. I think we're starting to get some promising results. There is lots of new things that now both fields, the large language models, right, which matured quite a bit, and autonomous agents can kind of help each other. So let's kind of go into the third part of the talk. But before I go, any questions here? Which one?
This one. So maybe I missed it, but how is it different from normal stuff? Or is it starting rate? How is the loss different from normal stuff?
So the yellow is the sec, the acceleration. So it basically maximizes, it spends most time at the edges. There is no gentle acceleration in the middle. Whereas both behavioral cloning and this combined method kind of have this slow acceleration. Also with the tires here, soft actor critic, more or less just most of that, it's uniformly.
Okay, I think I'll ask you.
We can talk more. Okay, so one thing with robotic systems and autonomous agents so far that really sucks, that's technical term, is task, it's task specification. Normally, the best case scenario that we specify tasks, like in these robotics things, is like 10 meters, in basically polar coordinates, 10 meters, 20 degrees off, and that's my goal. And in many other cases, reward is your task. And that means kind of adding terms and retraining the agent and seeing what's adding, and then adding more terms, and basically doing the endless reward shaping and so on. And that's not very useful. It's not gonna get RL or any of these methods kind of off the lab and in this more general setting. So one thing that I would much rather have, say for robot, is if I can say it, hey, how about pace forward fast? And it goes and it does this, right? Or go backwards, right? And slowly, and then kind of goes in and does that. That's more natural interaction, right? So how do we go about that? So in this case, basically we're saying that the interface is the foot pattern. So if the leg is in the contact with the ground, that's 1. If it's up, that's 0. You can kind of see the channel of zeros and 1. This is a busy slide, but let me kind of walk you through. There are 2 pieces to that. There is the controller. This would be your locomotion controller, and then blue path is the training path. This is the RL controller that takes the pattern and basically the sensory data from the robot and outputs the gait, basically the joint positions to produce the gait. And this pattern is basically this pattern of zeros and ones. And we train this again, like we randomly, back to the first or the visual navigation. We have this environment, we can kind of randomly generate the patterns, and robot's gonna learn to follow random patterns or not. And then at the test flow, we bring in the large language model, and we instruct it to be able to produce the foot patterns. I'll show that in the next slide. And then it produces the contact pattern, and then it's kind of being used, sent to a controller, and it executes that. So how do we instruct the LLMs? And this is GPT-4. You say you're a dog, your dog foot contact pattern expert. Your job is to give velocity and a foot contact pattern for this input, and there are here are a couple of examples. So basically using the few shot examples on how to do that. And then that's it. I mean, that's really all that's to it. But there are some surprising findings here. You can say, hey, back off, don't hurt that squirrel. And learns that gait, or does that gait. It says, active the ground is very hot. Now, why is that? That's surprising. And the reason is because the LLMs come in with these baked and pre-trained models of what one should walk when the ground is hot or so on. There's nothing about the gait there, right, and so on, but it's able to do this weird generalization, right, and produce the foot contact pattern just from kind of getting these few shot examples, right, and so on. And this can really revolutionize how we interact with the systems. Right now, my grandma can go and interact with the models. So LLMs bring a lot to the table for improving the interactions with the models. Second kind of thing that kind of prevents us from more generalization is that even kind of looking at these three models, or even within robotics, the action space is vastly different, right? Are you controlling them at the accelerator level, right? What are the joints, right, and so on. So without kind of having the uniform actions, that's kind of hard to create generalization beyond cross-domain. So to that end, actually, code is starting to emerge as a pretty good common pattern that, well, I mean, it can interact with the code. So back to our web agents, is our kind of one of the most recent work here, where it used to be kind of, okay, we're doing form filling, and I can say, hey, show me the way from San Jose to Mountain View with a second cycling map at the website, starting from google.com. And then it starts, basically types in the United States, produces the code, that code gets executed, next step is, okay, gets this, produces the next step, and so on until it selects the path. So now we're having natural language to code. How does that work? Well, again, starting with the URL, there is the human instruction and natural language instruction. We basically pre-trained a model here with self-supervision that takes the starting URL and the human instruction and outputs basically at the current context what is the relevant piece. You can kind of see it as a perception, and outputs a plan, set of smaller steps that one should do as the first shot. And it's going to get me an apartment in San Jose, search for condos, and so on. And then we take the view basically out of box LLM, in this case is Flamio Palm, that can take, okay, here's the HTML, here is the little simple instruction, produce me a code for that. That produces the code. We go and execute it. And then the way we train this now, it's in the loop. If the instruction fails, here's a compile error, right, and so on. Okay, that means that this plan or this instruction was not correct, so we can kind of update the plan and fine-tune or pre-train the model. And that then allows really good generalization across the task. Like, forget the form filling tasks. We can do evaluation for the real world web automation with 65 to 80% success rate with only 200 self-supervised samples. And this is on real estate, social media, and map websites. I'm going to say danger is here, and like we're doing this, like, oh my God, now we're sending basically code on the internet. So this is not going to see, this is not going to come out the lab. The code is there, right, and so on, and we're reporting it. But we need to also start thinking about the consequences of what we're doing here. Anyways, that brings us that LLMs bring universal actions and planning to the table. Out the box, more or less. They also have some interesting prompting properties. For example, turns out that the large enough models that are instruction fine-tuned, they actually represent the full distribution of the personality traits, and this is why we need to talk. They represent the full distribution of human personalities based on the Big Five inventory. Not only that, but with prompting only, we can prompt and change those personalities. Now, mind you, out of the box, turns out that the larger models are, the more bias they introduce. Because in okay, so if you're talking to a psychometrician, they'll tell you that certain personality traits are codependent and there is correlation. So if somebody's, I don't know, more extroverted, they're also, I don't know, less neurotic or so on. What large language models do, they do that, but they do it at a much more exaggerated scale, right? Okay, fine. But then we introduce basically prompting techniques where you can kind of tame them or you can kind of modify, say, hey, I want you to be very excited or so on. And this is kind of the graph on the left. And then on the right, we see that these personalities actually hold off and can be recognized with on the downstream task. In this case, this is a social media post. We ask it to generate 500 social media posts, and you can kind of see just the representation here of the words. And it's literally indistinguishable from, we're using the same test that they're using that psychologists are using for identifying human personalities based on the social media tests. So that's interesting. The second interesting kind of property of the large language models is this in-context learning. Raise hands if you know what in-context learning is. Okay. So in-context learning means, you guys played with LLMs, right? Yeah? All right. So I'm going to back a little bit more. With large language models, there are basically three phases. One is the pre-training, you kind of get some. There is the fine-tuning where you add more data and you can kind of improve on the model for whatever your use cases are. And then you run it in inference time where you have a prompt. And turns out when you have a prompt, and this was kind of example that I gave there for the dog, that you can provide it examples, or you can kind of give it more context, and so on. And there is no additional weights changing, right, and so on, but the model's behavior is going to change. It's going to learn new things and so on. So that's what's called in-context learning, because in that prompt window, you provided the context and it learns. So it's kind of been known this few-shot business, right? You give a few examples. I want you, here is my, I don't know, bio, tell me what certain things are, and here are two examples how to do this, or with the dog, right? Now with the large context windows that kind of recently became available, we can really scale up the number of examples we're giving. So this is what we're calling many-shot learning, not few-shot, but many-shot learning. So it turns out that, okay, if we're starting to have a large number of the samples, let's see, so yeah, if we, across different tasks, if we go from, say, 32 shots to 2,000 shots, the model's performance on that task improves. So the more samples you give, the models get better. So, okay, that's fine. We're getting into kind of traps, okay, where do you start getting this expert data and so on, but fine. Second interesting piece is that if you start telling it, if the model is pre-trained with, I don't know, notion that black is black and white is white, and you start giving it in the context examples and start labeling what's white black and what's black white, that it's going to start kind of catching on with that. So that would be your green line. The flip labels are the yellow line. Which means that with enough, this is one of these like a double-edged sword. If you have pre-training biases, you do not have enough data and so on, you can fix that in the inference time with kind of providing the samples. On the other hand, if you didn't have bias, somebody else can introduce your bias and kind of basically trick your model into flipping the labels. Now, third part is, and again, kind of more on the reinforcement learning, we don't need expert data, we're going to create our data, and so on. So when it gets to kind of really scaling up this plot here, we're talking 5,000 to 250,000 samples. That's a lot of samples. If you're going to have expert samples, right, that's a lot. So can we have model to generate its own samples? This would be your unsupervised in-context learning, so the green color, or the reinforced in-context learning is we ask model to generate its sample, and then we kind of use the reward to evaluate that sample. So not expert. The yellow is the ground truth, so this would be your expert samples. Well, turns out on certain tasks with a certain kind of levels, the unsupervised is even performing better than your expert samples. Go figure, right? And then reinforced ones are performing similarly and so on, or in some cases better. So we're hypothesizing that the reason for that is, again, back to that Goldilocks principle, that when the model it has enough of the prior knowledge baked in there, so when it proposes the new sample, it's closer to the distribution that it would expect to be useful for learning. Then when we kind of provide the expert sample, which might be too different than what model had expected. And I would love to see more theory behind it. This is kind of empirical observations that I think it's kind of warranted to be examined. And I'll just, again, these slides are 2 years old. The text to nerve, next to video, all these generative models, right, provide lots of possibilities for simulated environments. Just this drop, this is the fluid dynamics, which if you're going to do it computation, it's very, very expensive, right? But you can create this for learning, whether it's kind of precisely correct or not, maybe it doesn't matter. So the third area is this opens up, the LLMs really open up from the personalities where you can kind of start simulating humans and having behavioral sandboxes, right, where we can kind of simulate how humans are working, to kind of LLMs producing their own data and using generative models in simulation. There is the whole new space of the synthetic interactions. So what do we get when we put kind of all the pieces together? We have natural interactions, we have universal actions and planning, and we have synthetic interactions and self-play methods. We're starting to kind of we're getting into this self-improving loop where the models can kind of teach from themselves and generate its own samples and so on. And I think this is really where it's time for autonomous agents community that knew a lot about safety and so on to double down and bring its toolbox and tool set to the table. So how many of you guys know about the levels of driving autonomy? Okay, a few people. So there's this concept of the autonomous driving that say, hey, we can basically put the methods from level 0 automation to full automation. Level 0 means no automation. Human is driving. Level 5, it's a full autonomy. Everybody, like there is no human doing anything at any environment, no constraints. And then levels in between are. And the reason they kind of developed that is because then in the test case, they can certify car for this car is in level 4 autonomy. It's certified to operate only on the highways, or in these regions, right, and so on. Or this is the partial automation, we're just kind of having adaptive cruise control and so on. So it gives you a framework to say where you can certify the system and then what kind of the consequences of that should be. So we thought it would make sense to kind of talk about AGI in that sense. So we developed the levels of autonomy for AGI, levels of AGI. And the idea is that we can go from one side and we can kind of differentiate between narrow AI and general AI. So narrow AI would be, it does one thing well. Calculator, AlphaFold, right, from kind of different levels. General AI is kind of generalization to the max, does everything and anything. And then as you're kind of going through the levels, so level 0, no autonomy, your calculator is a good example of that, right? There is no AI, just 2 plus 2 and so on. The general level 0, no, it would be basically human in the loop. Human does all the thinking, right? There is no artificial intelligence to do that. But you can kind of do a variety of the tasks. And then kind of goes from there that we're basically seeing that ChatGPTs and so on, the current language models are emerging AGI, which basically acts as an unskilled human. And the level 2 would be that basically performs better than half of people or half of population, right? So that's kind of, we don't think we're quite there, right? I don't see anybody say, hey, the LLMs are better in this than kind of general tasks and so on. Whereas for the specific ones, yeah, we're kind of having some expert models, right, and so on. And then level 3 is really expert AGI. It's better than 90% of the human population. And then virtuoso 99%, and then level 5 being superhuman, and so on. So that kind of gives us a framework that if we have a model, right, we can kind of see from how narrow or broad it is and how skilled it is. What's interesting then is to look into how they can be used. So under level 0, human does everything. Under level 1, human is in control. Maybe AI does simple tasks and whatnot. Level 2, we can start getting consulted by human, but human still kind of has the substantive role. Level 3, we're kind of equal collaborators. Level 4, AI is starting to drive the interaction because it's expert, knows better than us. And then 5 is the full autonomy. We can also ask, so what are the societal risks to this? Well, level 1, maybe de-skilling, this disruption of the existing industry, right, and so on. 2, then you can kind of extrapolate for that. And then we can also ask, okay, for each one of these level of interactions, what kind of AI we need to have in place, or what kind of AI would enable this type of risks, and so on. So that kind of gives us a framework. It's a framework. There are many different ways to do it. I'll kind of have discussion on that, but let's have a discussion of how we evaluate these systems, right? What are the risks and how we go now and mitigate the risks ahead of time. So that's really kind of what's ahead of us. Let's kind of come together as a community, because it's both exciting times, kind of finally seeing all these places coming together, right? And then kind of let's kind of bring the levels of autonomy to place. So it was a long talk. Let me just kind of go back and summarize. First, we talked about specialized agents. And there's tons of methods and techniques there, from certain kind of objective functions, right, and so on, to enable efficient training, to clever construction of the simulation environments and whatnot, to enable efficient generalization, to kind of high quality generalization. And if you have application that needs one task and does that task well, by all means, you use one of these true and tried methods, right? That's what they're for. Then we talked about the emergence of the generalist agents, whether that's LLMs or kind of special or robotics foundation models or other foundation models. They can start doing like multiply tasks. Beyond that, kind of from the data-centric perspective, and how to go from requiring only expert data to really improving upon the data that was given. And then finally, we talked about the self-improving agents and how LLMs and autonomous agents can kind of play together, and where that kind of looks at the levels for AGI for the future. But I hope that the rest of the day is as happy as this dog that's learning just to it's going to go to a picnic. And with that, I want to thank everybody, and thank my collaborators. Questions?
I wanted to start with one question from Slido, which is, what is the difference between AGI and ACI? The superintelligence, artificial superintelligence, ACI, compared to AGI.
So AGI would be basically this whole right column of different levels of the AGI, and then superintelligence would be the general intelligence that performs better than all humans across many tasks, or like all the cognitive tasks.
Any questions from the room?
So maybe I'm going to ask one question. So currently you position like ChatGPT and existing models and the emerging part. And then on the next slide, if you don't mind, I think the emerging were like around like level 1 level. But like we can already see that models are being used to pretty much like manipulate on social media and quite a bit. There are like evidence that actually there are many like fake accounts that are driven by famous models. So when like the the more serious consequences are like put on the right side. On the scale, how should we look at this kind of application?
So that's a fair question, and has been. I mean, it's clear that even where LLMs are now, they are disruptive industry. So that's fine. The overtrust, targeted manipulation. I agree with you that we're kind of starting to see that with the level 2. That yeah, you need kind of emerging. You need emerging, which we kind of have. You're starting to kind of see targeted manipulation being sufficient for that. So I think like what are the ways to do that? We can do to fight against that is the regulations, right? That's one way to start putting. We can have vehicles that are not licensed and so on driving on the streets. Why should we have models that can be few shot prompted, right, or not evaluated well, being able to interact with the general public, for example. But it's a part of the conversation, right? Does that answer your question?
Yeah.
It's complicated. I mean, yeah.
I'm probably more worried now. It's a new piece I see of work, right?
Yeah.
It's yet to be published.
It's going to be presented next week at ICML. Yeah.
Any other questions? Yes. I have a question about perspective line question. So now, like people mainly apply LLM with robotics. So I see a lot of people using LLM as a high-level planner and then feeding to a low-level planner. So from my understanding about models like RT2, they train using Copy and POM, so to make POM E, and then that as a high-level planner, and then they train another model to map the coordinate from your perception, like the image, to a XY coordinate or something to perform the action directly. But how, like, well, as a human being, when I preserve about the environment, I can do like spatial reasoning, but from pure image-based observation, I can, and also you show the paper that uses the U tree, that's the code, and then you show the prompt, that's all text-based.
Yeah.
So from how I see it, these I can see there are many information blocks. What I can view is maybe it's interesting to try like 3D representation of the environment to give a better perception for the robot. Yeah. But here it introduces the model complexity, and when it's in real time, where the latency matters, it causes trouble. So what do you think is the next step for example, model like RT?
So there is lots of work kind of in providing data now, basically this perceptual data and so on, from robotics, autonomous driving, right, and so on, to the large language models or foundation models. So that's happening. But I think that kind of your first point, that has been maybe the largest collective surprise of the community, is how well things really work with so little information and text information. Back to the web agents, even this stuff kind of navigating the web pages, right, and so on, that's all text-based, based on the HTML. We kind of had some studies, there was paper, if you kind of add images, you might improve more, but not much. There's a number of other works, I mean, including the robotics, right, and so on, that most of these LLMs are trained from the data that's on the internet. I guess we talk a lot and we describe a lot. I mean, that's the only explanation that I have why it works, but it's been collective surprise.
Thank you for the presentation. I have a question. So you stated during the presentation that as more in-context learning examples you have, the performance increases, right? Would this performance converge at some point? because the context of large language model is limited, and also if the context is high now, like 1,000 tokens or something like this. Maybe there is more like a local attention than global attention.
Yeah, so again, this work was interesting from the empirical perspective because this was done on Gemini Pro 1.5 Pro, which has the large context window that, yeah, actually when you have a large enough context window, you can kind of keep compiling data and things are going to get better. Now, the next question really is, okay, now that we know that this is a possibility, can we actually be more disciplined and ask a question, given a fixed context window, whatever that might be, what is the best context to enable the in-context learning, right? And I mean, that's a open research area. It's a good question.
And also one more question. Those techniques, if you are at this slide, unsupervised in-context learning, reinforcement, example, have you tried combining them, like giving some ground truth examples and putting the large language model, simulate other examples and then predict, like having a mixture of those?
You can do like a self-play methods and so on. And I mean, to some extent, unsupervised methods are like the model generated.
Let's thank the speaker again.